Yo, yo, time for the next free response. 2019 number 4. Should be fun. So let's get to it. Boom. So here we go. I just realized I didn't share the screen. So let's try that again. Ready? Ready? Boom. Here we go. Of course, you've done this already. You better have done this already. If not, go do it. You got to do it yourself first before you watch me go over it. God. Kids. I'm just kidding. All right. It's weird because I'm alone in a room talking to myself. But anyways, so as you take this on the exam, right, read this twice. So I would read through this once. And once I read through this once, to me, I'm going to see things, some things jump out, right? So I want convincing statistical evidence. We're given an alpha level here of 0.05. So it should be pretty obvious that we're going to have to do some kind of hypothesis test. So now I'm going to go back and probably reread this context and think about, right, what do I need knowing that I'm going to be conducting a hypothesis test? So we want to know if there's convincing statistical evidence that there's been an increase in the proportion of all cochea, I don't know, plants that are resistant to glyphosate. This is not a good problem to choose to try to make myself sound smart on the internet. But anyways, we're going to have context that we're not familiar with on the exam, so I'll pretend that I just did that on purpose, when really I should have definitely looked up both those words prior to this video. But anyways, so as we think about this, we know we need a hypothesis test, right? We're given an alpha level. We want that convincing statistical evidence. So now the question becomes, which test am I going to use? So as I start to read through, right, we can see we have 2 samples of data. We've got some 2014 data here, so 61 randomly selected plants from 2014. And we've got some 2017 data, so we have 2 groups, and we're working with proportions. So this is our old pal, the 2 proportion z-test. So jumping in, right, we know we have a 4-step process: hypotheses, conditions, math, write our conclusion. So let's do it. Personally, I like to make myself a little table, start to summarize some information. So that's what you can see here. Where's my little head floating around? There it is. So 2014, 19.7% of 61 plants were resistant to that, to glyphosate or whatever. In 2017, 38.5% of 52 plants were resistant. We want to know if there's evidence that the percent that are resistant has increased. So is there evidence that the percent resistant in 2017 is bigger? Now, some of us might look at these 2 numbers and be like, yeah, 38.5 is bigger than 19.7%. Duh. But remember, these might just be different because of natural sampling variability. So we want to know if there's a statistically significant difference, and that's why we need our hypothesis test. Hopefully we remember, like, we're going to need some X values here when we go to enter everything in the calculator. Remember, P hat is the percent of the sample that, in this case, were resistant. X is going to represent the number that were resistant. And so remember, to find X, we need to find 19.7% of 61. And over here to find X, we need to find 38.5% of 52. And so if we do that, 0.197 times 61 gives us 12. And over here, 0.385 times 52 gives us 20. Remember that we have to round our X values to a whole number, because X represents the number of plants that were resistant, right? You can't have 20.02 plants being resistant to some thingy. When we go to write our hypotheses, we might start to use some 1s and 2s in our notation. And if we do that, we need a key. So for me, right, I like to use the table because now I can make this my key, right? This is group 1, this is group 2, or I could go little 1 here, little 1, 2, 2, 2, however you want to do it. But this table is one way to provide a key if you're going to use 1s and 2s in your hypotheses. So let's write those hypotheses. Anytime we have 2 samples, our null hypothesis is the same. In our null hypothesis, we're going to assume no difference in our percentages. Or if we had 2 sample t-tests, we would assume no difference in means. The idea would be the same. So we're going to assume that P1 is the same as P2. Or maybe for this problem, maybe it's easier to use P14 equals P17. So again, if I use the 1s and 2s, I need a key, right? Maybe the key is that table. Maybe the key is off to the side. I say something like this: P1 is the percent that are resistant in 2014, right? And P2 would be the percent that are resistant in 2017. Little side note, right? So P is the percent of all coquilla or cochia. I'm going to just pick one. I'm going to go coquilla. Hopefully that's right. P is the percent of all coquilla plants that are resistant. P hat is just the percent of the sample that were resistant, right? So P hat is a sample statistic. P is our population parameter. Another way we could write the null if we want to, right? We could actually write this as a difference. So we could say P1 minus P2 equals 0, or we could say P14 minus P17 equals 0, right? We're literally saying there's no difference in our two proportions. So you can write it the red way or the green way. You do what works for you. Calculator has lots of 1s and 2s in it. So myself, I think I would go with the 1s and 2s. It helps me to keep track of how I'm entering everything in the 2-prop z-test in my calculator. But at the same time, right, I could see why, you want to use 14s and 17s, because we forget a key, that's like a pretty big deal. So whatever, you do what works for you. Now for our alternative hypothesis, we want to know, is there evidence that the proportion of coquilla plants that are resistant to glyphosate has increased? So we want to know, is the percent in 14 less than the percent in 17? Or if I use the 1s and 2s the way I had labeled them, I want to know, is P1 less than P2? And again, this top, like that's what I'm going to see in my calculator. So that's why I tend to lean towards that, but whatever. Or we could say P1 minus P2 is less than 0, or P14 minus P17 is less than 0. The reason this is less than is if the percent in 2017, right, if there's a higher percent that are resistant, a smaller number minus a higher number is going to give us a negative difference. There's our null and our alternative written in a few ways. Oh no, I messed up my color scheme. Pretend these were all green. I'm sorry, Lou. I'm sorry, dude. Can't be messing up the color scheme in your color coding notes. So that's that, our null and our alternative. For me, my final exam, my answer on the exam is going to be this. Right, that's what I would use, right? But everything else, right, those are other options. You do what works for you. So that's step 1. Step 2, conditions. I know there's like a lot of them we got to check, but on the bright side, if we have to check conditions on our exam, like that's something we, even though it's a little tedious at times, I know that's something we should be able to get essentially correct. So, right, randomization, 10% condition, got success failure to check for each of these, and our independent groups. So moving over there, let me jump back to this little thingy. It's going to tell us we have random samples on the AP exam, right? And we see that somewhere here. Yeah, randomly selected, right? Randomly selected. So here we've got our conditions. So 1, all the plants were randomly selected, right? You can write that as one little sentence. You don't have to split it up. Next, 61's probably like pretty sure less than 10% of all coquilla plants in 2014. And then similarly, 52 is, right? These just mean like the same thing that's above it. So like, sure, do that, right? You're probably going to be handwriting this. You could type stuff. You do what works for you, but with the math, it might be easier, right? So 52 is likely less than 10% of all coquilla plants in 2017. They're just different colors because they're different conditions. I didn't want to blend them together. There's no like conceptual reason behind that. Then we got to check this one, our old buddy success failure. So N times P hat has to be bigger than 10 for both samples. And then N times 1 minus P hat, right? So if you're like, wait, where did 0.803 come from, right? That's just 1 minus 0.197. Where did 0.615 come from? That's just 1 minus 0.385. Maybe you notice here, and hopefully you do, that these are actually 61 times 0.197. That's how we got our X value. So this, we know would actually come out to be 12. So like if you said 12 is bigger than 10, that would also be correct. And over here, our number of successes was 20. So you could do like the green stuff that I just crossed out in parentheses, or you could use the actual numbers of successes and failures. Here there was a total of 61, so if 12 plants were resistant to glyphosate, that means 49, the rest of them were not. And here, if 20 of 52 plants were resistant, that means the other 32 were not. So whether you use the red numbers or the green, right, all good, all work for that condition. And then lastly, anytime we have two samples, we want independent groups. In this case, that means we want the percent that are resistant in 14 to be unrelated, to be independent from the percent that were resistant in 17. And there's no reason to believe those percents that are resistant are related because we have random samples. And that's what we're seeing here. So hypotheses, conditions, moving on. Let's see how we did. So this question was kind of weird the way they chunked it to me. I would have expected it to be scored as 4 sections, hypotheses, conditions, math, conclusion, but whatever. So they scored it in 3. So section 1, we need components 1 and 4 and at least one of the remaining. So hypotheses imply equality of proportions in the null and correct direction in the alternative. Using an appropriate population parameter in words or symbols, we did with our P with our little key, so we're good there. Let's jump right to 4 since that seems really important. 2 sample z-test for proportions identified by name or formula. We have not written that down, so we really haven't met that, although we said it out loud. And that's because many of us are going to copy this from our calculator screen, which is going to happen in a second. So this hasn't been formally written yet, but this is going to happen in a minute when we use our calculator. Identify parameters that are population proportions. Like, yeah, we kind of did by using P's, right? Like if you use P hats, you blew that. So, and we blew this actually too. And then both parameters are correctly defined as proportions of resistant plants in 2014, 2017, right? We did that in my black box with my key, which will be, like over there in a second. So let's jump into the math. So math-wise, I'm going to go back to our whiteboards. So here was us defining the parameters in context. First thing I'm doing, I'm grabbing my calculator. And we want to go to our stat tests. Clearly not a good idea for me to hold that. I apologize, that's kind of dark. We want our 2 proportion z-tests. So we want number 6. And then we're going to enter all that information from our table. So our x1, for me, I had 1 as the 2014 group. So x1 is 12, n1 is 61, x2 was 20, n2 was 52. We want to know if 1 is less than 2 because we want to know if 14 is less than 17, right? If the percent resistant here was smaller because we want to know if the percent increase got bigger in 2017. And then we're going to go to calculate. And so like the first thing I'm doing is copying down this screen. So 2 prop z-test. Now we got the name. That was that number 4 on the rubric we just looked at. I've got my z-score, negative 2.21. I've got my p-value for my conclusion, 0.014. And then I got a bunch of other stuff, right? I've got my 2 sample p-hats. Remember, this is our p-hat pool that we would use in the z-score formula. And if I scroll down, I would see the ends. I'm not going to copy all of those because I'm going to use those in the formula for this z-score. So we had 2 p-hats. Oh, sorry, I think I just broke my leg. So we had 0.197 and 0.385. Anytime we have 2 statistics, we look at the difference in them. This is always a 0 because we assumed no difference, right? So this is our statistic. We have 2 of them though, right? So stats, we find the difference, minus our parameter, which is always based on the null hypothesis. And then down here, I've got my standard error formula, which I'm gonna have to write like really small. This is gonna be 61 and 52. But remember, we said in our null, we were assuming that P1 and P2 were the same. So I don't want to use these 2 different numbers because then I'm going to contradict the assumption that P1 and P2 were the same in the null. And that's where this p-hat pooled is going to come into play. So this is going to be 0.283 and then 0.717, just 1 minus 0.283, and then another 0.283 and 0.717. And I'm pretty proud of myself for fitting that in there. And so that's how the z-score is calculated. If I want to add a picture, I could do that. I could go to draw on my calculator, but I don't really need to do that. I could just mark the z-score. So here's 1, 2, 3. So there's our z-score of negative 2.21, and we would shade to the left. We've shaded a pretty small area, which is reflected in my p-value, which is telling me I'm shading 1.4% of the curve. That's it. And I mean, honestly, you could have got, like, worst case scenario when you're taking the exam, if all this is tricky for you, like, just copy that, get some stuff, and then jump right to the conclusion. Because I know well, I'm pretty sure, I hope, don't make me cry, we all know how to write a conclusion, reject or fail to reject based on this p-value and our alpha level. All right. So there's our math. So back to our little slideshow here. Let's see what we got going on. What's next? So section 2. We need 1 and 2. So let's see. Notes the use of random samples. Got that. That's an easy one. We better never get that wrong. Number 2, checks approximate normality by showing the expected numbers of resistant and non-resistant cochea plants are both larger than 5 or 10. This is that success-failure condition we checked. We're good there. Notes the populations must be extremely large or satisfying the 10% condition. We did that. Correct value of the z-score, the z-test statistic, we got that. Correct p-value, we got that. E, strong E, because we got all 5 of these hit. And then hopefully you're like, dude, it never told me I had to show that z-score formula. Relax. I want you guys to, I'm trying to get 5s here and understand everything. I'm trying to do the bare minimum. Off my back. All right. Let's finish this up with our perfect score. All we got to do is write the conclusion. No big deal at all. P-value was 0.014, so the p-value of 0.014 is below the alpha level of 0.05, so we reject the null hypothesis, right? P is below alpha, reject the null, and if we reject the null, there is evidence. And now I'm actually going to jump back. I'm going to come back to here. I'm going to steal this. So when we're writing this, let's just take the wording out of the question, right? What were we trying to find evidence of? We were trying to decide if there's evidence that there's been an increase in the proportion of all cochea plants that are resistant to glyphosate, right? That's what I'm going to write. Don't make it harder on yourself. Don't use any extra brain power. That's what we were trying to prove. Just copy that wording right from the question. There is evidence that there has been an increase in the proportion of all cochea plants that are resistant to glyphosate. Ignore the typos. Come on, I'm rushing here. That's it. Come on, you know that's perfect, but let's look at the rubric anyways. Let's look at the rubric anyways. All right, there we go. So, provides correct justification of the conclusion, comparing p-value and alpha. Done. P-value is below P-value is below alpha, so we got that. Correct conclusion. Yup. Reject the null. Context. Yup. Just copy out of the question. There is evidence of that. There's been an increase in the proportion of all cochea plants that are resistant to glyphosate. This is one we can get a perfect score on. I mean, we can get a perfect score on all of them if we come ready for the exam. But this one, we got this. So, one more to go this week, and then next week this stuff starts for real. We'll talk more about that, but hang in there. Miss y'all. Next video coming up in a second.